Good day, everyone. In this video, I'm going to tackle down 8 important topics of data structures and algorithm. So firstly, we have array. What is an array? An array is a data structure that stores items in a fixed size, continuous block of memory. Think of an array like a low, oh, exit. Think of an array like a long row of cabinets. Each cabinet has a number, and inside it is a value. Because of the cabinet are placed in a straight line, we can open any cabinet instantly if we know the number. This is why array access is big O of 1 or or constant time. But it's not perfect. It also has weaknesses. When you want to insert or remove something in the middle, you have to remove you have to move all the cabinets or array or a binary like the values after it, which takes big O of n time. Second, linked list. A linked list is a linked list is a structure made of nodes. Each node has the data plus a pointer to the next node. So imagine a chain where each link holds some information and also points to the next link. This makes adding or removing link very easy. Just reconnecting the chain. That's why insert and delete are big O of 1 if done at the head. But accessing something is slower because we cannot jump to it. We must follow the chain link by link. So searching or accessing is big O of n. Thirdly, we have array list. An array list is a dynamic array that can automatically grow in size. Think of it as an array that repairs itself when it gets full. If you add too many items, it creates a bigger array and copies the old items into it. Accessing is fast, big, big O of 1. Adding it to the end is usually big O of 1, but if a resize happens, it becomes big O of n. Deleting and inserting in the middle are also big O of n because of shifting. Space is big O of n, but arrays sometimes have an extra unused space. Fourth, stack. A stack is a data structure that follows the LIFO rule. LIFO means last in, first out. So basically, it's like stacks of plates. You can always put a new plate on top, and you always remove the top plate first. You cannot remove it from the middle nor the bottom. There are three basic operations of stack: push, pop, and peek. Push is to add a value on top, add something on the top, add a plate on top. Pop, remove the plate on top. Peek, look at the plate's value. All of these are big O of 1 time because you can only deal with the top element. Fifth, queue. A queue is a structure that follows the FIFO rule. Instead of FIFO means first in, first out. A works especially like a queue, like a line of people in a store. The first person in line is always the first to be served. The, the two basic actions of queue. In queue and DQ. In queue, add to the back, and DQ, remove from the front. Both actions take big O of 1 time. So it's like how queue in real life works. So you're using queue anywhere, like you doing in a playlist. Six is trees. No, it's not a tree that you see outside. This is a data structures. So at so at, so what is a tree in data structures? A data structure. What is a tree in data structure? A tree is a hierarchical structure made of nodes with a root on the top and a children below. Like that's why it's called a tree because it looks like a tree, but it data. Think of a family tree. You start from one ancestor, aka the root, and then more members to grow from it. Common type of the common type of this is binary search tree. Left child has smaller values, right child has larger values. This let us search faster. If the tree is balanced, search, insert, and delete become big O of big O of log n. If the tree is unbalanced, it becomes big O of n. 7 is graph. A graph is a structure that shows relationship between objects using vertices and edges. Think of a map. Cities are vertices and the roads between them are edges. Like Blender. If you ever use Blender, you will know what I'm talking about edges and vertices. There are two ways to store graphs. Adjacent, Adjacency matrix. A grid that shows if a connection exists uses big O, B square space. First to the check, pass to check connected, big O of 1. Secondly, secondly, adjacent list stores only neighbor stores only neighbors of each nodes. Uses big O, B plus E space. More efficient for large graphs. And lastly, sorting algorithms. Sorting algorithms arrange data in order, usually from the smallest and largest, like any sort sorting works. Sorting helps us search faster and organize data. Here are the common values. There are bubble sort, bubble sort, simple but slow, selection with bubble sort, simple but slow, big O of n squared. Selection sort, always big O of n squared. Insertion sort, good for small lists, best on big O of n, worst on big O of n squared. Merge sort, fast and predictable, big of n log n, space big O of n. Quick sort, fast on average, on big O of n log n, worst on big O of n squared. Keep sort, always on big O and log n, space is big O on big O of 1. These algorithms help arrange data more efficiently. So lastly, we have dim sort. It's a hybrid sorting algorithm that combines insertion and merge sort to get the best performance. It is a default sorting algorithm by Python and Java. Think of a dim sort like this. It first divides the array into small pieces called runs. It sorts each small runs using insertion sort because small arrays are faster than sort way. Then it merges the runs together using merge sort, which is very efficient for combining sorted lists. This combination makes them sort fast and stable for almost real world data.